we now have an effective procedure for figuring out whether a square matrix is invertible or not. And that is, do row operations until you get to a row-reduced echelon form matrix. If you can get to the identity, your matrix is invertible, and if you can't, then your matrix wasn't invertible. But it still raises the question of how do we actually find the inverse of a matrix when that inverse does exist? To figure out how to do that, it helps to think a little bit about exactly what problem you're solving when you look for the inverse of a matrix. So let's think about the 3 by 3 case. Let's say we wanted the inverse of a 3 by 3 matrix A. So that would be a matrix B, which in particular satisfied this equality. We know a little bit about how matrix multiplication works. One of the things we learned was that matrix multiplication works column-wise, in the sense that if you write the columns of B as C1, and then C2, and then C3, then the result of this matrix product is the matrix whose first column is AC1, and the second column is AC2, and the third column is AC3. So if you want this to be the identity matrix, then what you need to do is to solve the matrix equations AX equals the first column of the identity, which is 1, 0, 0, and the matrix equation AX equals the second column of the identity, and AX equals the third column of the identity, because a solution to this one would be the first column, C1, of your inverse. And the solution to the second one would tell you what the second column of your inverse ought to be. And the solution to the third one would tell you what the third column of your inverse ought to be. So if a matrix is invertible, then you can actually find what its inverse is by solving matrix equations. And we know how to solve matrix equations. We've got our row-reduced echelon form procedure for doing that. So the final thing we're going to do in this part of 0005 is to look at how to compute the inverse of an invertible matrix using our row-reduced echelon form procedure. But before that, I want to tell you something about 3 by 3 inverses. You've seen a formula for the inverse of a 2 by 2 matrix. It was quite simple. It was fairly straightforward to use, to the extent that if you had a 2 by 2 matrix, the quickest way to figure out its inverse would simply be to use the 2 by 2 inverse formula. So it's very natural to ask, is there a similar formula for 3 by 3 matrices? And the answer is, well, yes, but you don't necessarily want to use it. So just for fun, I don't expect anybody to remember this, but just for fun, here is the formula for the inverse of a 3 by 3 invertible matrix. If A is a 3 by 3 matrix whose ij entry is A, little a subscript ij, then A inverse is 1 over delta times this matrix here, where the notation I'm using is that this expression here with two straight lines at the side means the determinant of the matrix A, B, C, D. So for example, this thing here would mean A22 times A33 minus A23 times A32. And delta here is this horrible expression, so A11 times A22 times A33 plus A12 times A23 times A31 plus, and so on. Okay, so my point in showing you this formula is not that it is any practical use to you in computing inverses, but rather to illustrate that being able to compute inverses in a different way is truly valuable to us, because nobody wants to have to use this awful formula. So here is how we find inverses to matrices practically. In fact, what our procedure is going to do is not only determine the inverse of a matrix, but it will also determine whether that matrix is invertible. So this procedure is for finding the inverse, if it exists, of a square matrix A. Step 1 is you form an augmented matrix A with the identity to the right of it. So I've called that a super augmented matrix, because you don't just add one extra column, you add a whole extra matrix on the right. The reason to do that is because, as we saw on the initial slide, what you're trying to do when you find the inverse is to solve a lot of matrix equations at once. You want to solve the matrix equation AX equals first column of the identity matrix. You want to solve the matrix equation AX equals second column of the identity matrix, and so on. So rather than solve those things separately, which we would do by forming an ordinary augmented matrix, we'll solve them all at once by forming a super augmented matrix where we add all those columns at once on the right of A. Once we've done that, we do some row operations to put this thing into row reduced echelon form. Then if you get the identity matrix then something else, that means that A is invertible and its inverse is B. On the other hand, if you don't, so if the first part of the matrix, which you get by putting your super augmented matrix into row reduced echelon form, is not the identity, then your matrix A was not invertible. So this is now a simple and an actually practical procedure that you could do by hand to determine invertibility of a matrix, and if it is invertible, to find its inverse. You simply form this super augmented matrix here, and then you put that, or you do row operations until you've got a row reduced echelon form matrix, and if the first half of your row reduced echelon form matrix is the identity, then the second half is the inverse of your matrix, and if the first half was not the identity, then your matrix that you started off with wasn't invertible. Let's do an example of this in the 2 by 2 case. So we'll take A to be the matrix 1, 2, 3, 4. To find whether A is invertible, and if so, to find what its inverse is, what we do is we form our super augmented matrix, which is obtained by taking A and then sticking the 2 by 2 identity on the right, and we put that into row reduced echelon form by doing row ops. So here is the matrix you get by putting the 2 by 2 matrix, the 2 by 2 identity matrix on the right of your matrix A. And you can see there that's exactly what I've done. You now need to put that in row reduced echelon form. So let's look for the first reason why that's not in row reduced echelon form. The first and the most obvious reason is that there is a leading entry in row 1, just here, but the other entries in the same column as that leading entry are not 0. In a row reduced echelon form matrix, every entry in the same column as a leading entry must be 0. So we need to eliminate this 3 just here. And we can do that by subtracting 3 times row 1 from row 2. So that's our first row operation here. Subtract 3 times row 1 from row 2. When you do that, this is the matrix that you end up with. You can see row 1 hasn't changed. Row 2 now has a 0 in the column of the leading entry in row 1. Now we're not in row reduced echelon form yet, and one of the reasons we're not in row reduced echelon form is that there is a leading entry in row 2 which is not 1. In a row reduced echelon form matrix, every leading entry must be equal to 1. So in order to get that leading entry to be 1, what we'll do is multiply row 2 by -1/2. That's what we do with our second row operation here. We're multiplying row 2 by -1/2. You can see again row 1 hasn't changed. Row 2 now has its leading entry equal to 1, and so we're one step closer to being in row reduced echelon form. However, you can see that there is an entry in the column of the leading entry in row 2 which is not 0, namely this 2 here. We need to eliminate that. We need to make it into 0. So we do that by subtracting 2 times row 2 from row 1. When you do that, here is the matrix you end up with, and you are now in row reduced echelon form. You can see that all 4 parts of the definition of row reduced echelon form are satisfied. There are no 0 rows, so that part of the definition is met. There are 2 leading entries in rows 1 and row 2, and they're both equal to 1. Each leading entry has every other entry in that column equal to 0. And finally, the leading entry in row 2 is to the right of the leading entry in row 1. So we've met all 4 conditions for row reduced echelon form, and we're finished. Now, what we found was that the first part, so this part of our matrix, is the 2 by 2 identity. That means that our original matrix was invertible, and the second part will be equal to the inverse of A. So the inverse of A is equal to the second part of our super augmented matrix, which is now -2, 1, 3 over 2 minus 1 over 2. You can check, if you like, by hand that that really is the inverse of A.